Patrick is at the University of Antwerp, and he's been on our podcast a couple of times. We actually met him through Pierre. Pierre actually said, hey, there's this young guy who's doing some incredible work on liquid plasmas. And we were like, liquid plasmas, what the heck is that? We got to talk to this guy. You know, Patrick's really opened my mind up about how enormous of a bin this concept of plasma is. Perhaps so enormous that it's exceeded its utility. But at the same time, something interesting does happen to matter, and it does possess. Even different phases of matter seem to possess the ability to become conductive under certain temperature and pressure regimes. And Patrick has just done an incredible job of helping me understand that, and Anastasia too. He's also done a ton of work for this conference to make it happen. So I'm so grateful to have Patrick on the team this year. I hope he'll be here next year. And it's really been wonderful to do this with somebody and not just be the two of us alone. So anyways, Patrick Vanraes, he is going to talk to you about cold fusion in a liquid sun. Perfect follow-up. Here we go, Patrick Vanraes.
Yeah, thanks, Shaila, for this introduction, and the gratitude is completely mutual. So I want to thank you for inviting me and giving me the chance to talk about this topic, because this was really Shaila's and Anastasia requests to talk about the liquid model of the sun. I will combine, actually, the liquid model of the sun. I have to go closer? Yeah, okay. So I think I can imagine. I will actually combine here the liquid model of the sun as proposed by Pierre Marie Robitaille with two other models. One of them designed by me a couple of years ago, the multi-plasma model. So here you see Pierre Marie standing in front of his liquid model. And I think it's safe to say by now that his liquid metallic hydrogen model of the sun is the most promising non-standard solar model out there. I will not try to convince you of this claim. If you're interested in it, I would say look at his videos, look at especially this paper by him about the 40 lines of evidence. So you have a lot of experimental evidence that he points to there. Now, today, I will just want to give you a little bit of a taste on what this model of his can do. He's very often saying that his model has so many advantages compared to the standard gaseous model of the sun. And this is going to be an illustration of that for fusion specifically, fusion reactions. So let's get to a little comparison between these two models, the gaseous model and the liquid model at the left and the right respectively. So I want you to focus here, especially on the values of the temperature and the density in the solar core. So at the top there of the graph. In the gaseous model, you see that you have immense values of 15 million Kelvin and 150 grams per cubic centimeter. So that's 150 times the density of water here on Earth. These are completely different values than the ones that you see in the liquid model, which are way milder. So according to Pierre, you don't have even close to temperatures of millions of degrees there. We don't know the exact value, but let's say they should be, according to Pierre, low enough to still have a lattice, still have condensed matter. And that is not possible with such high values, according to him. And then density is also very mild, 2 to 3 times as dense as water here on Earth. So quite mild values compared to the gaseous model. And that gives a little bit of a problem to the liquid model, but you can also see it as an opportunity. So what is fusion exactly? It's bringing two cores together and fusing them into one, which is hard to do because they're both positively charged, and you have to overcome this Coulomb barrier. In the gaseous model, this is not so much of a problem because basically the makers of this model assumed the core of the sun to be hot enough and dense enough to do it. But in the liquid model, you need new mechanisms to do it. And so, Alexander, here we go. This is how you can explain in a dense material, how you can have this fusion reactions. So Pierre, wait, this one is a bit too fast. Okay, whatever. Some of my animations do not seem to work. Pierre proposes mostly these three mechanisms at the top of the slide. The lattice confinement, so that means you have your atoms close enough together because they're in the lattice. Then lattice vibrations, which means you have heat, at least some amount of heat that makes them move towards each other, and so they can fuse in the end. And very important, the bias shielding, which makes this process easier. More about that later. This is due to conduction electrons in the metallic material. And then you also have these two auxiliary processes, the internal pressure near the core and convection currents near the surface, but they are a little bit outside the scope of this presentation, so I will not focus on them. So here you have another proposal of Pierre. This is the exact lattice that he wants. This is not really due to fusion. This is because of the radiative properties of the sun. He says there is only one possibility according to him, and that is this hexagonal planar lattice. This one is the least problematic from all of the choices that we have. So let's use this one. And then this one has a semi-metallic or metallic behavior because the electrons are being delocalized in the planes of this structure. And because of that, you will have very strong planes where you can focus all your energy on. And so you can have the atoms moving in the planes according to Pierre, making it easier for them to ultimately fuse together. Now, do I dare to do it? Yes. I will try to argue that Pierre might be wrong here, that fusion does not necessarily have to take place in the planes, because that's what Pierre thinks is the main mechanism here. And then a little bit also about the reaction products, because fusion reactions are having different products, and then some of them, for example, helium, do not fit in these planes anymore. They cannot bind with the neighboring atoms. So you have to have a place where they can go to, and this is then between the layers, the intercalate layers, as they are called. And this can be the birthplace of all elements according to Pierre Marie's model. And then you will have a buildup of all of these reaction products from the fusion, which in the end will create immense pressure in these intercalate regions, which can then explain why the sun has some of these violent reactions, such as solar flares, but also less violent ones, such as solar wind, expelling this material. So that is Pierre's perspective summarized on how fusion takes place in the sun. And very often you hear, when you see comments on Pierre's videos from his opponents, like, oh, he's the only one thinking about this. But actually, very interesting to know is that he's not alone in this view anymore. There are several researchers out there who, maybe not in the context of the solar model, but at least in terms of experiments in the laboratory on solids, have a very similar perspective. And so here there is a group from Metzler et al. From the Massachusetts Institute of Technology, which have made a really very recommended review paper on how to think of cold fusion in solids in the lab. So they have taken 3 fields of physics together: atomic physics, nuclear physics, and quantum dynamics, to explain why you can have, in theory, fusion at ambient conditions, at low temperatures. Let's start with atomic physics. So here you will regard the fusion process, the two cores that you want to fuse, as 2 points: point charges, point masses. And accordingly, you will have this interatomic potential, the Coulomb barrier that you see here, this line. That's the barrier you want to cross, coming from the right to the left. And then the red arrow that you see there is the energy that you need to cross this barrier, which can be smaller than the height of the barrier, the green arrow V. Why? Because you have something called quantum tunneling, which can cause your particles basically to tunnel together and in the end fuse. But so, as you can see here in the last line of the slide, most attempts of technologically relevant fusion focus mainly on making E bigger, the red arrow bigger, and not on making the green arrow smaller. And how can you make the green arrow smaller? By Debye shielding. So imagine two cores isolate in an isolated region of space, which you want to fuse. This is very, very hard to do because they are positively charged and they will repulse each other very, very much. But imagine these two same cores now in a sea of negative charge, such as delocalized electrons. All of a sudden, this repulsion is way less strong and your fusion process will be way easier. Less repulsion, lower Coulomb barrier. And this is the basic principle behind how to have fusion in cold conditions in a condensed state. So, Alexander, here is basically the answer to your question, to your comment. But so we can go a little bit more in detail on it. So, in their article, they make this figure, Metzler's group, and the most important part about this figure to understand is you want to get in the gray region. These are the ambient conditions. And then this line shows you the orders of magnitude that you need to cross of the probability of your fusion process, the two cores being fused together. And you can see by what I just said, you can already cross this immense region of orders of magnitude to get very close to, rather close, I would say, still many, many orders of magnitude away, but quite close already to this gray zone. And they propose even an extra atomic physics mechanism, which you don't have to read this quote, it's a bit technical, but which summarizes to lattice imperfections provide for higher screening. Defects in the lattice can make your fusion process easier. And that's where I think Pierre might be mistaken. The fusion processes might be easier around defects in the lattice than in the planes of the lattice. Very interesting for the liquid model of the sun. Then we can go to nuclear physics, but I will be very short about this because what does nuclear physics do? Here you will look at the intranuclear structure of your cores. So more like what's happening in the core itself, how does it look like? But yeah, if you have two protons, they are so elementary, there's not so much of substructure there, apart from maybe the very complex things that we don't understand yet so much. But so for protons, this is a little bit less important than for the, let's say, more complex cores. But so in the end, you can have intranuclear resonances that can increase the chances at certain energies to have this fusion process. But now let's go to quantum dynamics, and here is where the real fun begins. So as you can see already in the figure there, you have a big area that this quantum mechanics can cross because you have such a rich variety of mechanisms that you can think of there. Most important here is that here in this field, you will consider the fusion process as a quantum state transition. What does that mean? If you're a bit familiar with quantum mechanics, you will know about spontaneous emission. So you have a higher energy state that decays towards a lower energy state and radiates energy in the process. Your fusion process can be looked upon just like that. The higher energy state are your two separate cores. The lower energy state is their merged product, the fused core. And the radiation process, that's exactly your fusion process, radiating away its energy with light and particles. And then you can go to more complex quantum dynamics, involve quantum coherent effects, and come to the conclusion that you can make this spontaneous emission process stimulated and way faster you can make your fusion process more probable. And so you can do this with, for example, thinking about resonant energy transfer, or short RET. But this is more like you have two very similar states, which then hybridize with each other, which is way faster than this spontaneous emission, but there is no emission there. So you need to combine it with another process, such as super radiance, and then you get a very fancy named process, a super transfer, or you can also call it super radiant ret or Dike enhanced ret, where you actually involve the quantum coherent effects from the environment, where they absorb part of the energy, make this process way faster, and make it ultimately possible to cross this many orders of magnitude. And then a very interesting thing that Metzler's group mentions here is that within these quantum effects, you can also begin to consider quasi-particles or collective excitations such as phonons, plasmons, and magnons. And that's where my model comes into play, the multi-plasma model, because this one is all about these quasi-particles or collective excitations. I won't explain you exactly all the details about this, but just imagine for a moment that these collective excitations are waves in your material. For example, the waves of the ions and the waves of the electrons being present there. Then you begin to talk about phonons and plasmons. You can also do something like that with magnons. And so basically the multiplasma model describes an excited state of your material. Electronically excited, vibrationally excited, magnetically excited. And it does so by considering different layers, different subsystems, thermodynamic subsystems, which all agree with certain degrees of freedom of the same type. So, for example, all the phonons, all the plasmons in different subsystems. And then you're going to look at the coupling between the systems, which occurs on different time scales. So some of these systems can transfer energy towards each other very quickly, others will be very slowly. And then you also might see, it's too small probably to see, but you have this molecular degrees of freedom that I also made in this original version of my model. You can say, like, we don't have models in the solar body. Why does this matter? Here, just replace the molecules with defects in your lattice with the particles that you have in the intercalate zones or in vacancies, and you can actually keep the same model structure for this purpose. So here we come back to this idea of Metzler et al. That his group from Massachusetts Institute of Technology, that all of this thermal processes, this plasmons and this, well, let's say especially the phonons, they are quite slow in time if you compare it to the fusion reactions. So what you can imagine to happen here in this model is you will have at certain places, for example, close to defects, sometimes the perfect conditions because of the plasmons, because of the phonons working together by coincidence stochastically, creating the perfect conditions for fusion, where two cores near each other that can try many times to fuse and ultimately create fusion on quite ambient conditions. Now, this makes this whole multiplasma model very interesting, and especially like individual subsystems and all the coupling between them to be investigated for the purpose of fusion in the condensed state. And then I want to also quickly note two extra parts that Metzler's group is forgetting about, and I think are very important in this context. You also have something called non-thermal phase transitions. And this is, for example, if you electrically excite your material, you will have an ultra-fast excitation in some cases. You can do this with ultra-fast lasers, for example. Then you can have a contraction of your material, especially if your material is metallic. That's called phonon hardening. This happens on very fast time scales. contraction of your lattice is exactly what you want in the case of fusion. So this is a very, very important process to consider as well. And then finally, also a little word about the importance of electrical currents in your system, because electrical currents, intense currents, they can also be considered as a type of electrical excitation. So this is a very attractive way to create conditions which might be very favorable for fusion reactions. And indeed, there have been experiments already in the lab that shows that at quite ambient conditions, you can have fusion reactions induced by electrical currents. So, oh yeah, before I forget, think about the sun having magnetic fields. Where do magnetic fields typically come from? We know here on Earth, it's typically always, well, mostly generated by electrical currents. So this is very, very relevant also for the solar world. So in summary, we have this combination of these three fields: atomic physics, nuclear physics, and quantum dynamics, that you can combine to have all of this very interesting fusion mechanisms in condensed state. Then you can involve this quasi-particle physics, as in the multiplasma model, which opens the door to a very rich description of all of this lattice confinement fusion mechanisms. And then we also have to take into consideration the effect of defects, non-thermal phase transitions, and electrical current, which can play a very interesting and perhaps even dominant role in this fusion process in the sun and in the laboratory at ambient conditions. And these mechanisms apply quite in a straightforward way to Pierre Marie's model of the sun. So voila, here you have it.
So I would actually ask everyone to hold their questions. And so Patrick is going to give a second talk right now.
I'm sorry for the ugly background picture, but this is also perhaps an ugly topic to talk about. From the title, you might think that I will talk here about a lot about the Earth's oceans and how they are the source of the CMB, but actually I'm going to talk more about the subtitle here: the biggest threat to the standard cosmological model. Alexander, again, after the rest, you were yesterday asking a very interesting question. Is the standard cosmological model falsifiable? The answer is a resounding yes. And I will show you in this presentation why it is and how we can falsify it. This is a comment that I found under one of Pierre Marie Robitaille's videos about this topic. So all of this presentation is based on Pierre Marie Robitaille's work. And this comment really resonated with me quite a lot. So I think if you want to be more successful in persuading the university physicists, then you should stick to fewer arguments. When you hammer 20 different points, it becomes too much for some people to take in. They will therefore ignore all of your arguments. Stick to 2 to 3 bulletproof arguments. And I think that's really important in Pierre Marie Robitaille's case, because he has so many ideas, it's sometimes very hard to see the forest for the trees. So, let's start with the beginning. This is a quote from the European Space Agency website. Penzias and Wilson, two radio astronomers in the United States, registered a signal in their radio telescopes that could not be attributed to any precise source in the sky. It apparently came from everywhere, with the same intensity, day or night, summer or winter. Scientists considered their discovery as solid evidence for the Big Bang theory. However, nearby there was a body of water. Water can be a very good microwave radiation emitter. Microwaves can scatter in the atmosphere and end up in the horn antenna that they were using. So, where is this solid evidence exactly? Because you have another very good explanation for it. However, Not everybody agrees with this type of reasoning, as you can see here in this comment that I found on the Physics Stack Exchange about Pierre Marie's work, because nobody in the scientific literature is really citing any of Pierre Marie Robitaille's work, so I have to work with places like this, with comments like this. So the explanation that oceans are the source of the CMB makes no sense. WMAP and Planck probes have seen CMB coming from all directions when they were 1.5 million kilometers away from the Earth. Oceans cannot radiate into a detector that is so far away and looking away from the Earth. Seems like a very reasonable counter-argument against Pierre's assumption that comes from the oceans. And here a second one that I found on ResearchGate, I think also quite a, let's say, a reasonable source. The central proof that the CMB is not due to water on Earth arises from the SZ effect, with more than 30 independent experiments and results. In short, we directly observe the CMB being influenced by the hot gas in the distant galaxy clusters. Due to scattering with high energy electrons, the CMB signal becomes slightly boosted in temperature, and this proves that the CMB is a background source behind distant clusters and galaxies rather than from any local origin. Seems hard to argue with. So, welcome to my masterclass on how to defeat the CMB and most of standard cosmology. How do we deal with this criticism? Let's get back to the basics. The CMB is the strongest pillar from the Big Bang theory. Redshift and light element abundance are the two other pillars, but they cannot manage to hold the Big Bang theory on their own. Take away the CMB and the whole model falls apart. So I would argue, no, it's not the strongest pillar. The CMB is the weakest link. Because if you can defeat the CMB, you can defeat the Big Bang theory, you can defeat standard cosmology. So now I will talk a little bit about what the CMB is exactly, why it likely comes from the oceans, and why it likely comes from outer space. If you're confused right now, that's exactly the problem, because the CMB stands for two things that are very often confused with each other. Two signals, two microwave background signals that are measured typically with different instruments. Namely, the black body microwave backgrounds, I will call it the BMB, just to make it very clear that it's different from the other one. And this is what they also call the monopole in astrophysics. So this is, let's say, everything that has to do with this black body radiation. And then the fluctuations on this black body radiation, that's the A and B, the anisotropic microwave backgrounds, typically presented with this anisotropy maps. These are the multipoles that they very often talk about in terms of the CMB. Very important to make this distinction between BMB and AMB. And now you can resolve this picture a little bit further. You can now see that the BMB is the strongest pillar of the Big Bang theory. Because if you take away the BMB, the A and B with the other two pillars are not strong enough to hold the Big Bang theory. And by the way, this is nothing, there is absolutely nothing controversial about this. You can ask ChatGPT and it will completely agree with you. You can just take whatever standard cosmologists from the street. They will agree with you. It's the BMB that really should matter here. The black body radiation. If A and B is not coupled to black body radiation, your whole model collapses. So, the BMB is the weakest link for the Big Bang theory. Very important conclusion. Because now we get to we can simplify the discussion quite a bit. The A and B on its own does not provide any direct evidence for the Big Bang theory. So, the discussion should focus completely on the BMB with regards to, let's say, criticism on Pierre's work. So these two comments from the internet, we can just discard them in the garbage bin because they focus on the A and B, which does not provide you any direct evidence for a hot Big Bang. It only provides you evidence for microwave background fluctuations without a black body. So let's just not talk about this part anymore, like, oh, a part of the CMB comes from outer space. Let's focus on the BMB. Let's focus on the BMB possibly coming from the oceans. So here Pierre is differing from the standard cosmologists. So European Space Agency and NASA, they are, and all standard cosmologists are very much agreeing that both the BMB and the AMB are from the same origin, namely the Big Bang, relic radiation from the Big Bang. While Pierre says like, no, you have to split them up. And the BMB comes from the oceans, and the AMB, I paraphrased here a bit, it's an ill-defined space signal. I think that kind of captures what he means with it. He says like, no, it doesn't make sense at all. Just don't think about it. It's nonsense. But I try to at least give here a little bit of perspective, like it still might come from space somehow. And then here's the real kicker. You don't have any direct evidence that BMB comes from space. And that's where the argument basically should end. But most cosmologists still believe there is this evidence. So let's break it down a bit. Here I try to summarize most of the measurements that have been done. So in 4 categories, you have the earthly detectors, you have then 3 satellites, COBE, WMAP, and Planck. And very important to know is where they are located. The earthly detectors are obviously located at Earth, then COBE very close to Earth, 900 kilometers is close enough to still have access to this radiation from the oceans. And then you have WMAP and Planck, which are located at the second Lagrangian point, which is 1.5 million kilometers away, as we already saw in one of these comments before. So that's a little bit too far away to receive this radiation from the oceans. So that's exactly what Pierre Marie also says. The first 2 categories of instruments, COBE and the earthly detectors, can measure the BMB because they're close enough to Earth, while WMAP and Planck, they cannot measure it because the second Lagrangian point is way too far away. And so here you see a summary of what these instruments were measuring. So nothing special about the first row there. This is exactly what Pierre Marie Robitaille said in the previous slide. Earthly detectors and COBE can measure the BMB, WMAP and Planck, they cannot. They were not even designed to do it, so nothing really special about it. So here, let's have a look at the symbols. A green V means that it was measured. Red cross means it was unable, the instrument was just unable to measure it, or was just not designed to measure it. And then the red flag is problem for the Big Bang theory. It should have measured it in principle. Then it's a little bit more complicated than just direct measurement of the BMB, because you also have something like an indirect measurement through the dipole, one of the multipoles. And this dipole is the first derivative of the monopole. So in principle, you can calculate the monopole from it. And there you see that only COBE was actually measuring the BMB in that way. But there is a little red flag there. Why? Because through these 2 methods, the direct method and the indirect method, they were measuring different temperatures. And significantly different, because look at the error bars. Look at the errors at these numbers. They're so small because this was one of the most perfect measurements of a black body. Actually, the most perfect one that humans ever performed. So these error bars, they don't overlap, and this is actually quite significant. So here is a quote from Pierre. These uncertainties are at the 1 sigma level. The difference between these 2 numbers remain highly significant even at the 99% confidence level. So this is a problem for cosmologists. And even this indirect measurement does not prove that the BNB comes from Earth at all. So it's actually just a little red flag. I would not consider this to be as significant as the other red flags that we will discuss immediately. Then you have also this comment on criticism on Pierre Marie's work. The COBE probe was located much closer to the Earth, 900 kilometers above the surface. It was measuring only in the direction away from the Earth. Very important. So its measurements are consistent with those done by WMAP and Planck. So the relative proximity of the oceans had no impact on the results. Seems like a reasonable comment until you begin to think a little bit more according to physics. So this is this COBE satellite. Very important is this gray shield that we will immediately talk about. And then you have NASA saying things like, the far infrared absolute spectrophotometer, so this FIRAS that you see in the picture, instrument precisely measured the spectrum of the cosmic microwave background, showing that it matched a black body, a perfect emitter and absorber with a temperature of 2.725 Kelvin, providing strong support for a hot cosmic origin. COBE had produced the first baby picture of the cosmos. Statement, no doubt about it anymore. However, there is something called diffraction. The effects of single diffraction in two FIRAS, while considering the Sun-Earth radio frequency shield, so this gray thing there, were neither measured nor appropriately computed. Diffraction of earthly signals into the FIRAS horn could explain the spectral frequency dependence first observed by the FIRAS team. So COBE doesn't prove anything about the origin of the universe. The signal that it measured could just come from Earth through diffraction. So where, again, is our solid evidence? Where is this baby cosmos? And yeah, I have to come up with new flags because a red flag is not really appropriate for this one. So I thought maybe we should use a baby blue flag to symbolize the argument's maturity. Like, oh, COBE is a good argument for the Big Bang. So here we get it. Two blue flags with the early detectors and COBE because they did not exclude any earthly sources in their experiments. They cannot prove these experiments. They cannot prove that the BNB did not come from Earth. But then you still have these other two red flags. The WMAP and Planck satellites, which had differential systems analogous to the DMR on COBE, should have been able to measure a dipole. And if so, we should be able to calculate the value of the monopole at the second Lagrangian point. But unfortunately, that never happened. Instead, the teams from WMAP and Planck, they used the data of COBE to calibrate their dipole. This tells you a lot about how trustworthy they think their own instrument is. They cannot even isolate the dipole from it and say, like, we're now going to compare it with COBE and see how well they compare. This is, I think, a red flag already. And so to summarize, the early detectors and COBE are inconclusive about the BNB origin, and WMAP and Planck, they only focused on the A and B, so they cannot really be used as a strong argument in favor of the Big Bang theory. But here comes the real kicker. There is one detector on Earth, the Heruni antenna, which provided very strong counter-evidence against the Big Bang theory. And you can read it all in this paper and other papers written by Professor Heruni. So the title says itself, measured parameters of large antenna of ROT 54 2.6, so that's the Heruni antenna, tell about the absence of the Big Bang. The paper gets citations on Google Scholar, 2 citations in total. I checked some of the other papers of Haruni on this topic, 0 citations. Why should we ignore this solid counter-evidence? What are standard cosmologists doing? Science or wishful thinking? And so here are the conclusions. The best way to disprove the standard cosmological model, Alexander, is to disprove that the BMB would come from outer space. Currently, there is no evidence whatsoever that the BMB would come from outer space, in direct contradiction with claims from NASA, the European Space Agency, and the majority of cosmologists. Instead, Haruni's antenna provided clear counter-evidence. The measurements of the CMB are some of the best examples of what is known in the philosophy of science as theory-ladenness. So, one of the best examples of this one can find in the history of science. Standard cosmologists clearly had no interest up to now to falsify their own model, only to support it. Is this science or is this something else? And so I want to really invite all standard cosmologists that are listening, or all even non-standard cosmologists that are listening and would not agree with any of my statements. And please send me an email to tell me why. I'm also just learning. I'm not a cosmologist. I'm a philosopher of science, traveling in this area and seeing a lot of problems. Can you teach me where I'm wrong with my reasoning? Because I cannot find it, and I don't think you can. So I'm convinced this theory is no science. Prove me wrong. There's my email address, or you can leave a comment in the comments of the video. I will certainly read them, I will process them, I will treat them fairly, but obviously I will treat arguments from authority and ad hominem arguments in a different way than reasonable arguments.
All right, it's time, Alexander.
I wanted this to be a lot when you read the subject. So I start with your last talk, agreement. I think you have pointed out multiple issues with the CMB. I don't believe this is a strong color as broad as you depicted it. And I think there are multiple issues with the CMB, data correction, filtering, galactic foreground, low surface brightness energies, whatever. So it's really not that reliable. The hypothesis of Pierre that it comes from the ocean, I think he worked it out very well. It's terrific work. In total, I might be a little bit agnostic about it, but I think in general, the skepticism of the CMB should not hinge on the acceptance of the claim that it comes from the oceans, because it is more contentious, right? So we might even leave that apart and destroy the CMB evidence in other means. That's my comment. And well, I wouldn't call it non-science. It's okay. It's science. But you might. The important point I think you might, they didn't repeat the monopole, if I correctly understood the argument. The Planck and measurements, the subsequent measurements did not repeat the monopole measurement, and that's great. That's missing. Okay, your first talk. Now comes my disagreeable version of my story. I think the visionary idea of Pierre, the sun might be a liquid metallic hydrogen, great. The agreement, fantastic. But coming back to my points, visionary idea mathematically formless. You absolutely need that. You need calculations that justify that. So what I did, a very modest contribution, but I made it also to convince myself of the model. I made a calculation. Can we achieve the necessary pressure to transform hydrogen into a metallic state from the chromosphere above, by assuming that the chromosphere is liquid but molecular hydrogen? Okay, so I made a calculation, and it's called the liquid metallic hydrogen modeling the chromosphere, and I found something interesting. And you can see that there is a transition, there is a certain pressure where it's more comfortable for hydrogen to stay in the liquid metallic state rather than in the liquid molecular state. Okay, so I'm not saying this right, this is a good paper, but just people need to work in that direction, modeling concretely, quantitatively. Physics is quantitative. And for that reason, I have my doubts that the interior of the sun is kind of that metallic structure, whatever it is, because it just does not add up. So according to my calculation, I'm not saying it's right, but just come up with another one, says that necessarily the density goes up, and well, it's just, you said that there are a density of 2 or 3 grams per centimeter. Sorry, but I won't believe that number until I have seen the calculation. You need to do these kind of calculations. So this is the skeptic point of view in this direction. And well, remark, we are fighting a battle in the inside of the sun here. And while the rest of the world is still unconvinced about the surface, for which I think there is pretty good evidence that it's a liquid metallic hydrogen. But my final question in this direction would be, why do you need that battle in the interior of the sun? I mean, is there really a need to abandon the conventional mechanisms of fusions, high energy, high densities, high temperature at the core of the sun? Is there really a need to abandon that? And at the same time, you can keep the surface at the metallic state? That would be nice. Thanks for your patience.
I'm pretty sure Pierre would answer yes, there is certainly a need to keep it condensed matter in the core. But your other question, is it necessary to have this battle from a philosophical point of view? I think it's maybe indeed, if we don't want to have too much of discussion about this and already just want to bring the main message to the world, to avoid such discussions. Just to simplify the message. But Pierre Marie thought about this quite carefully, and so his opinion about this is pretty strong. So one of the things is liquid metallic hydrogen is known to have typical density in certain states, so 0.7 grams per cubic centimeters. So that's what Pierre Marie Robitaille expects at the surface of the sun, and then you can begin to use the average density of the sun, which is 1.4 grams per cubic centimeters. So you need to, at some point, end up with a conclusion like, yeah, you need more denser material towards the core.
Can I add that Pierre also points to the solid body rotation at the core of the sun?
Yes.
As well as
And I think that would be his strongest argument. Like, we need a solid core or a condensed core because of Helios cosmology.
Can we get another question?
I can also try to counter or reply on the CMB part. I think you're correct that we should focus not so much on why does it come from the oceans. It's a very interesting discussion, but this is, in my opinion, is a secondary discussion. We should really focus on, look, guys, you really didn't do the experiments in a way that you would falsify your model. You only used the satellites and all these instruments to try to verify it and get some data supporting your model. But you didn't even try to falsify it and to show that this radiation actually comes from outer space.
Thank you very much, Patrick. It was an excellent presentation of the CMB. I want to ask you a question about something that you did not talk about that I think is, when I've talked about the CMB, it is kind of like my number one thing to talk about. And that is when you do Earth sensing satellites, the satellites, as I understand it, use the CMB, the 2.7, as their reference. And they get that not by looking up at the distant black body that's supposed to be up there, but instead they get it by looking at the limb of the Earth, and that's one of the Robitaille's last videos. And I thought it made the strongest case for it. And I was wondering if you have any comments on that. I know it wasn't part of your presentation.
I think you bring up a good point, and this is actually very, very interesting information. But I would not include it in the primary discussion for people trying to disprove Pierre Marie's work, because it becomes just a little bit too complex to explain it. The reason why is, if you work at the limb of the Earth, and also the signal you get if you turn satellites detectors towards the Earth, you get a mixed signal. And that's where the confusion starts. So you will have this discussion like, oh, the signal is completely different from this 2.7 Kelvin thing. We can tell all we want, like, look, you're mixing two signals. You're mixing what you call the BMB, or what they call the CMB, this black body radiation with a temperature of 2.7 Kelvin with radiation coming from the hydroxyl bonds. So in the water, according to Pierre, you have two decoupled radiation systems, the hydrogen bonds and the hydroxyl bonds. And both of them radiate, and both of them have this mixed signal when you point your detectors towards the Earth. And there it becomes really complex to convince non-standard cosmologists, I think, that, look, you have to have a more complex picture. And then their reasoning with looking at the limb of the sun actually makes sense, because they expect their radiation to come from outer space. So why not, what I'm saying, limb of the Earth, not of the sun. If you look at the limb of the Earth, that's exactly where you would expect to start measuring as a standard cosmologist, where you would start measuring your CMB. So it's a complicated discussion there to convince non-standard cosmologists, standard cosmologists.
I want to remind everybody too, we're going to do a panel tonight on the CMB, so we're going to go deep into all of this again. So let's take maybe one, maybe two quick more questions so we can not get too far behind schedule here, and then we will go deep this evening on this as well.
It's not correct that the WMAP and Planck has not detected the monopoly. Of course, the monopoly is there. The thing is that in COVID, there was an instrument, the FIRAS, especially designed to measure with high accuracy the monopoly. This is why it was published, the monopoly in the 90s with the COVID. But the monopoly is already detected in the WMAP and the Planck. Also, there are other ways. You mentioned that the Sanger-Selvovich effect. There are other ways to confirm that there is some radiation of 2.7 Kelvin out in the space, the transitions of some molecules in the space, or, as I said, the Sanger-Selvovich. You need, it's not only the anisotropies, you need a 2.7 Kelvin radiation in order to produce these transitions. If you do the calculation, it's impossible. Only with the 1 in 1 million fluctuation of the anisotropies, you cannot produce this Sanger-Selvovich effect. So I totally disagree with your point that there is not anything in the outer space of 2.7 Kelvin radiation there. I know we have not much time. I'm not going to describe this idea of the radiation of the ocean, but think that the black body radiation is a perfect black body, 1 in 500, 400, and the atmosphere has some irregularities. Even if the ocean is producing some part of this radiation, you cannot produce this level of the black body radiation. And even for the COBE, which is 900 kilometers, even forget about it, it's impossible. Even with all the things that you have mentioned, the diffraction and all that. It's, I say, something for discussion now, we can discuss by email or whatever. Just to remark also my impression, my opinion on that about Robitaille's works. He used to publish in a journal, which is not even a journal. Progress in Physics is not a journal. You go to there's a list of all the publications, reference journals in physics. There are 1,200 journals in physics. Progress in Physics is not in this list either. It's just a web page where maybe somebody have a look or just publish it. I think it's not the publications of Robitaille are not controlled by anybody.
We're controlling it right now, I would say. So this discussion going on right now, that's the control. And I think, sorry to interrupt you, by the way, I think I really want to invite you and everybody listening who thinks the same way as you. Send me this evidence that WMAP and Planck have measured the monopole. Because Google Scholar already disagrees with you. If you try to find articles saying literally like the monopole has been measured by WMAP or the monopole has been measured by Planck, a simple search will show you that nobody seems to agree with you in articles which are peer-reviewed.
The monopole is there. The thing is that
How do you know?
But the monopole was measured by COBE. It's a different level.
But COBE measured the monopole in accordance with Pierre Marie Robitaille's arguments. He said you have this diffraction still possible at that point to measure the BNB, the black body radiation. And COBE is, of course, a little bit of a tricky part because it measured both the BNB and the ANB. The ANB comes from outer space. The BNB does not come out of outer space. It comes from the oceans, according to Pierre Marie Robitaille's model. And that's where this discussion can become very complex. But so there is no proof whatsoever. And I really challenge you, give me the evidence. There is no evidence that WMAP and Planck have ever measured a monopole. They even didn't try to give a temperature for the monopole based on their dipole. How is that not alarming?
because the instrument was not designed to measure with better accuracy than the COBE. COBE has a specific instrument, the Vanraes, to better. It was not the mission, but the monopole is there.
Yes, and here we come to the point. These satellites were never designed to measure the monopole. They were never interested in measuring the monopole.
The satellite that was designed to measured it in space.
No, they were not. They were measured. They were designed to measure the anisotropy maps.
It's true, that is true.
COBE
First instruments to increase the sensitivity, but they had monopole signals in each of the detector, but it was not at the accuracy of COBE. So they were more focusing on a differential signal, which was to be measured with the higher accuracy. That's why they didn't call the monopole, but it was measured.
I think the
Individual antenna signal monopole is there.
send me the articles, because the point here is that Planck, yes, could have measured the monopole in principle, but it never did. They never published any value for the temperature. They never tried to show that it's a black body radiation. Show me the evidence. It is not there. If it is there, you should easily be able to send me a paper where it is there.
All right, guys. The good news is we have. Let's take one more question because you're lined up already. This will be the last one. We need to move on, otherwise we're eating into the rest of the program.
I have 5 one-line comment questions, and it'll take much less time. H2 molecule has a lot of electron density in between the protons. If you're going to argue that device shielding increases the probability of fusion, you need to argue that there's a lot more electron density in between the protons, and I'm not seeing how you do that. Symmetry considerations may have some effect on which reactions are more easy than others, be similar to the Woodward-Confinement rules in organic chemistry. You can talk to me about that. If there's a lot of free neutrons, we don't need to worry about electrostatic repulsion because they will just hit things. Second talk, you kind of ignore the dipole. The dipole looks like a blue shift in the direction that the Earth is moving and a red shift in the direction we're moving away from. And I'm having a lot of trouble understanding how oceans, which are at rest relative to the detectors, could generate a blue shift, red shift dipole signal. And finally, the idea that diffraction is affecting the Pharos measurements is testable. We can just send a beam from the Earth at the COBE satellite and see if it gets detected. So there's an experiment that you could do there. Thank you.
I will start from the way back because I think that's the easiest for me to remember. I'm not sure how easy it is to send a signal at the right frequencies to have it detected at COBE, but if this is possible, this would be an interesting thing to do. But I think we should not just single Pierre Marie Robitaille's theory out with a single experiment. There is much more work to do here to prove the Big Bang theory. And that's the point. We should not just focus on details here. We should focus on just the fact that there is no solid evidence for this monopole coming from outer space. And then your comment about the dipole, you're perfectly correct. The dipole is part of the multipoles. It's part of the A and B. It can come from outer space. That's not in contradiction at all with the B and B coming from Earth. So you can calculate that. So where is this radiation coming from? From the galaxies sending out some microwave signals. Obviously, the whole theory about the dipole remains the same there, whether it is black body radiation or not. And that's the problem. As long as your A and B cannot be coupled to black body radiation, you have a problem. You don't have a Big Bang. You need the black body radiation. The direct measurements of the B and B, the direct measurement of the dipole, the monopole, that's the important one. The indirect measurement through the dipole actually doesn't prove anything. It just proves that you have a signal coming from outer space which has this Doppler shift. This.
The dipole assumes the monopole is measured on Earth, is what you're saying, basically.
It's an assumption. It's not a direct measurement.
All right, man, Patrick. Let's give you a break.